It's my great pleasure to introduce for our last session today, our speaker, Mateja Jamnik. Mateja is a professor of artificial intelligence in the Department of Computer Science and Technology at the University of Cambridge, and also an associate fellow here at the Leverhulme Centre for the Future of Intelligence. She's also served as a specialist advisor to the House of Lords Select Committee on AI, and founded the Women at CL initiative, which supports women in computing research. And in her research, she's interested in human intuitive reasoning and making computers think intuitively, too, by building computational models that capture human reasoning in an attempt to humanize computer thinking. And we're delighted to have her with us today to speak about AI and society, the thinking machines.
Oh, thank you very much, Ali. I trust that everybody is seeing the actual presentation. So I was just wondering, with the show of hands, if you can put like the thing up, where the thumbs up. How many of you are computer scientists? I'm trying to gauge what kind of audience I have here. Let me see. It's a bit tricky when you're.
I can see two thumbs up so far.
You see two.
Yeah.
Okay. And how many of you are philosophers? Oh, quite a few. Okay.
Yeah.
How many of you are cognitive scientists? Two, am I right? Okay, and the rest? I don't know what else. I guess it would be engineers and psychologists. Okay, so predominantly, I get a sense that we have philosophers here today. So I'm going to talk today to you about, well, the workshop is about the kinds of intelligence. And since I work in artificial intelligence, and I'm particularly interested in human thinking, I'm not so interested in machines, but I'm interested in humans, and I'm trying to model the human thinking and the types of things that we would consider to be intelligent, and in particular intuitive, when a human does it. If we saw that behavior on machines, we would think that too. So I'm trying to model those kinds of inherently human traits of thinking and intelligence on machines by building systems that can do that kind of reasoning. And whilst this talk is going to be very accessible, I am very happy for people to stop me and ask me questions or save them for the end, wherever you want. And I can go to huge levels of technical detail if you are interested, or small levels of technical details. I'll just give you the flavor today of the type of work that I do and the things that I'm interested in and the things that I'm researching with my team in the Department of Computer Science and Technology here in Cambridge. So, and that's why I entitled this talk is a slightly more generic about AI and society and the impact of the intelligence in these systems on the society and our everyday lives, and particularly how do we create these kinds of thinking machines. Whoops. And this one I have obviously. Okay, there we go. So when we are dealing with everyday objects, we love to pretend that objects are like people. And so we treat them like that. We give them names, we talk to them, we even get attached to them. And I'm giving here a picture of Tom Hanks in the film called Castaway, and he's talking to his friend, which is a volleyball, and he calls it Wilson. But when it comes to computers, I mean, how would we feel if the machines were thinking like us? And if they were thinking like us, one day perhaps they could think better than us. In fact, I would argue that to a certain extent, in certain specialized areas, they're already doing that. And I'll give you some examples of that later on. So these are the sorts of questions that people, because I work in AI, people keep asking me, how far are we away from, you're building these intelligent machines, how far are we away from being outsmarted by them? And where is AI now? And basically throughout my career, I have been looking at how people think and studying the kinds of intelligence that people demonstrate, in particular, things that we would consider intuitive. So let me start by saying a little bit more about what we mean when we say AI. And I'm sure that all of you have seen these almost daily headlines that we see now in the newspaper. So for example, we read that DeepMind computer is beating the champion in Go, in the game of Go. We have self-driving cars that are regularly being now driven on our streets or tested on our streets. We have AI tutors that are replacing teachers, and films like Ex Machina and Blade Runner portray our future as being populated with robots that are indistinguishable from humans. And I guess one of the questions that has been brought up earlier on is what is general AI? And I think that probably the most common agreement about that definition, not that there's that much agreement, is that these are machines that can behave and act in ways that are indistinguishable from humans. So what does the future of AI really hold for us? So I'll start. I want to take you back and a few years when I was a kid. And when I was at school, I really, really loved maths. And what really fascinated me was not just that how systematic everything was, but there was a beauty and elegance in the solutions that we were seeing. But sometimes I was even able to find some of these beautiful solutions even by myself. So, but I was also interested in people. So I wondered, how do people come up with solutions like that, with such beautiful, intuitive answers? And as I was going through my university degree and then started my job, I started to investigate this kind of human thinking, this kind of human intelligence. And I got essentially really frustrated by the fact that I always had to work with machines in the way that was dictated by machines. They didn't work with me the way I wanted to work them with me. So let me give you an example. Like, why can't my sat nav understand that, I've been in Cambridge for donkey's years now, and that telling me to turn left at the round church and then right after the big supermarket in town is far more helpful to me than saying, turn left in 250 meters, then turn right in 50 meters, then left again in 300 meters. So in my work, I want to make machines that do just that, basically. I want computers to work with humans in intuitive ways, and I want them to find solutions that are intuitive for humans. And so let me give you an example of what I mean by intuitive human reasoning. So here is a checkerboard, and it's called a mutilated checkerboard because it's got these two diagonal corners missing. Now, a very famous question asks, can you cover this mutilated checkerboard with dominoes? And so now there are many combinations of how we could try to do this. And one way is like this. So we could start tiling it in this very systematic way, left to right. And what happens? Well, we cannot cover it. Maybe we could try to do it like this. So I'm going now round and round, being clever, trying to fill it up. And again, I can't do it. Okay, so now think about how about if I color my checkerboard, and if I color it black and white like a chessboard, right? So now I'm using this representation of a checkerboard. And so a domino is covered with one black and one white square. And we've taken, and the same with the board, but we've taken two diagonal corners away, which means in this particular case, the ones that I took away are two white corners. So obviously I have more black squares than I have white. But in order for me to cover this checkerboard with dominoes, I would have to have the same number of black and white squares. So obviously, I cannot cover this mutilated checkerboard with dominoes. And this is something so easy for people to see and understand. There's no symbols, no algebra, no numbers. I'm essentially done. And I can understand why this kind of explanation holds true. Now, how would a machine go about solving this problem? Well, there you have it. Here is a proof of, I think it's in Isabel, or maybe it's in Hull. It's one of the theorem provers. There's lots of symbols, lots of algebra, lots of mathematical concepts, and it's not very intelligible. And the intuition of the human solution is completely lost in it. Machines can't really capture this kind of intuitive thinking. Not yet. So this is the sort of thing that really fascinates me. How do we get machines to emulate this kind of human thinking, this kind of human intelligence? So let me go and just say a few words about what AI is striving to do and why is it so hot today. So AI has always tried to achieve machine thinking and behavior that is indistinguishable from a human. So this sometimes is referred to as general AI. And so, but what does it make AI such a hot topic now? And I'm not talking about AI just from the machine learning point of view. I'm talking about AI in general. And I think that there are three major advances that have enabled us to make such huge progress in AI. And they are, first, the availability of masses of data that we generate all the time, then the supercomputing power that we have, and third, more new and more sophisticated machine learning algorithms that perhaps we haven't considered before. So in terms of data, every click we make is recorded somewhere. Every video we watch, every item we buy online, everything we say to our friends on social media. So, and this data is really valuable because it provides us insight, not about just us individually, but so that we can be offered these personalized recommendations, like the films that we might like. But more interestingly, it provides us with an insight about the behavior of groups of people. And that's really valuable when we are trying to understand human behavior and impact of intelligent behavior on society. Computing power. Well, we can rent it, for example, from any one of Amazon's data centers really cheaply and get access to probably nowadays even more than 80,000 servers. And just to give you a comparison, the Watson computer that beat the human Jeopardy way back in 2011 used 90 servers. So, you know, and now we have at our fingertips, we have instant access to massive computing power. And third, it's the new machine learning algorithms that are at the heart of what I refer to as AI revolution. So unlike in the past, when we were building these really specialized software, like really specialized, they knew about the problems and tried to solve very specific problems. Today's machine learning algorithms really know nothing about the problem, but they only know about how to learn. All they do is spot patterns and learn patterns. So for example, let's have a look at the autocorrect on your phone. So like ages ago, in the very early days, if you made a spelling mistake, it was very rarely picked up. And also you had to misspell things in particular ways. And this was because there were particular rules that the system knew about, and they were very specialized, and you only recognized those. Today, I can type into my phone in my native language, in Slovenian, and even though my phone knows nothing about it, it will still learn how I use Slovene spelling and words, and in fact, even learn how I misspelled Slovene words. So that's really interesting. So because it seems, in some way, it seems rather counterintuitive, because we have these learning systems that are really general in that they can take any data and crunch it to find patterns. In fact, any problem that we can recast as a statistical algorithm working over huge amounts of data can now be basically revisited and again viewed in with the new creative approaches of today's algorithms. So these are the three advances in data. These are the three advances in AI. So data, computing power, and algorithms that are at the root of this so-called AI revolution. So you may wonder, what can AI already do for us? And of course, everybody is talking to their Alexas, HomePods, phones, sat navs, etc., etc. And we at home have the very first generation, in fact, and the kids use them to spell things, broadcast news, play music, find recipes, time our cooking, and kids also like to ask them to jokes and stuff like that. Then of course we buy stuff from these assistants. So speech recognition and natural language understanding and processing research has made huge leaps forward and huge advances. And it's not only that they've improved the ability to discern speech from ambient noise, but also to place recognized words in the correct context and even guess words because of the meaning of the entire passage of speech. So machine learning and huge data sets have enabled these algorithms to reach accuracy rates of around 95%. And of course, we're all buying online. We are all getting our films and music recommended to us. And basically, these platforms now learn about our behavior and about our tastes and habits and so on. And they can even help you find your partner. No, I didn't meet my husband online because it didn't exist at the time. So AI is also used for in environment, for sustainability applications. So Google, for example, deployed machine learning algorithms to reduce the amount of energy that its data centers are consuming by like 40%. Smart traffic signaling can reduce congestion and pollution. You might have heard or might even have some smart lighting in your house or offices. So basically, AI already and intelligent behavior and the intelligence of the kind that we would consider intelligent in a human being is already part of our lives, and it's essentially becoming ubiquitous. But there are still massive, whilst there was this massive progress, there are still huge challenges that remain. And basically in achieving what's sometimes referred to as general AI. So a flexible, adaptable learning, self-improving system that can perform all the tasks that a human can in ways that are indistinguishable from a human. So here I'm giving you what I think is a definition of general AI, because we heard in the previous talk what is the definition of AI, or what is a definition of intelligence. So currently AI systems are super fast at processing huge amounts of data that very much exceeds human capabilities, but they do so in really specialized and singular tasks in ways that are machine-oriented and most of the time are incomprehensible to us and to humans. And one of the abilities that they lack is this human-like thinking that we could call intuitive thinking. So computers think fast, but not intuitively, not yet anyway. So let me give you, this brings me back basically to my love of maths and people and to my work. So in my work, I really ask myself several questions, but here is one of them. How can we make machines that understand us and think and work with us intuitively? And to find answers, I analyze what humans know and how they solve mathematical problems in intuitive ways. So using what we would perhaps call eureka steps. So for example, with using diagrams. And then in my research group, I go away and I program computers to work with us in these kinds of personalized ways and to help us solve problems in the same way that we would solve them, in ways that we would do it. So here is one example. Let me ask you a question. What is an area of a parallelogram? How would you compute it? So why don't you click with thumbs up if you can remember this from school? I'll have a quick look if I can see on the side. Who remembers this, or who actually knows what it is? Just thumbs up. No, come on. Nobody. Oh, there we go. Oh, yes, great. Okay, we have some. Fantastic. So how would you go about computing this? There we go. Well, here, if you were an expert, then you might perhaps do it like this. Take an integral and do this. If you are a primary school child, then maybe you will go about it like this. So you are covering it with unit squares. Or if you were an average person, then you would perhaps use a diagram like this. So it's width times height. And you can see why, right? So of course, the second solution is not accurate, the child solution, the primary school, but it's a start. And it's at least an approximation that eventually, as one becomes an expert, could lead you to understand the Einstein, the integral solution. And the last solution is visual, and it gives us the intuition of the area of a parallelogram. So it's clear that it's the product of its width and its height. And we can clearly see why that is the case. So in my work, I analyze different users, like experts, novices, average users, and different possible ways of solving problems. Like, for example, I showed you here 3 different methods. One was not particularly accurate, but it was a start. And then I built computers that choose these personalized ways of working with us in these kinds of, in ways that are intuitive to us. Okay, and I can say a lot more about that in technical detail if anybody's interested. Now, this brings me to my second question, which is, how can we build machines that find solutions that we think are intuitive? Okay, so here is an example. What is the sum of all consecutive numbers up to any chosen number? So let's see, let's try it for numbers up to, say, 27. So, okay, 1 + 2 + 3 + 4 + 5 + 6. Okay, no, I'll be here forever. So I can tell you that the sum is 351, but I didn't sum all the numbers one by one. Instead, I used a theorem, and I used this theorem. So you can see that the sum of the first natural numbers is n times n + 1 divided by 2. So first, so how would we go about solving this? You might remember this theorem from maths classes when you were at school, and even my kids are now learning this at school. And actually, let me ask, who can remember this solution from their school days? Let me have a look on your. Oh, great. Okay, fantastic. So you were taught this theorem in school. Let me jog your memory, and I'll show you how I was taught this at school. So we used a diagram, and we used this diagram. So first of all, natural numbers are positive whole numbers. So let's represent them using counters. So let's draw a rectangle that is n counters wide and n plus 1 counters high. So this gives us basically the first multiplier, so the denominator, which was n times n plus 1. And you will see that in my picture, I chose that n is 5. So I have a rectangle that is 5 counters wide and 6 counters high. And now this represents my n times n plus 1. Now, let me split this rectangle kind of down the diagonal. You can see that what happens is that I get two identical triangles. And each of the triangles is n counters tall. So in my picture, this would be 5 counters tall. So my next step is, now I'll just take one of these triangles, because one side of the equation for my theorem was n times n plus 1 divided by 2. So I'm taking half of my original picture, so just one triangle. So now I have this triangle that represents the right-hand side of my theorem, of my problem. So the next step I would do is, if I start splitting this triangle down like this, and I continue doing this, I get a succession of increasing natural numbers. So our triangle shows that 1 plus 2 plus 3 plus 4 plus 5 equals 5 times 5 plus 1 divided by 2, which is 15. So now notice that I showed you a concrete example for where n equals to 5, and we proved the theorem. But we can also see that whatever number I take, say n being 27 or 99 or 1001, the solution will still be the same. And more than that, we can also see that it's a correct solution, right? And so I want to capture this kind of intuition on machines. So in my work, I designed and implemented a system which could solve problems using diagrams in precisely this kind of way. Spatial manipulations are the inference steps of the solution, and I use formal methods to justify and why and also how a concrete case of a diagram, so in this case n equals to 5, and a concrete solution can capture the general solution for any n, so for any number, for the universally quantified theorem. And finally, if a solution is found, then the system will guarantee that it's a correct solution. So obviously, this is really important. If we are applying these intelligent systems in safety critical applications, we have to have certain guarantees that the solutions that they're finding us are correct solutions. So I showed you that we can make computers solve problems in the same kind of way that humans do it. But I was also wondering if machines could discover new, unseen intuitive solutions to problems that people have not been able to understand or solve before. And in order to tackle this, we use AI methods like machine learning that I mentioned earlier. So far, I looked at solving problems in mathematics, but the idea of intuitive thinking is general and can be applied to any area of human endeavor. And this is where I'm focusing my energies and work next at the moment. So we're making machines discover new knowledge, new intuitive human-like solutions to problems. So let me say a little bit more about where we apply these. So this kind of work that I do is really quite foundational, right? We are making computational models, but we take them then and apply them in really quite practical areas. So I'd like to expose you to 2 areas of which I think where this disruptive AI technology has, in my opinion, the biggest impact, and where I'm really applying this foundational work. So first of all, in education and AI tutors. So with researchers turning to investigate human capabilities and building these into AI systems, which are then intelligence, then intelligent, emphatic, and dynamically responsive AI tutors could become a reality. They gauge our personality traits, our mood, our speed of learning, our level of expertise, and then they tailor their interaction with us to us. So we are devising profiling protocols in my work that can gauge the level of expertise of human users. And we then apply these algorithms to choose the right representation of the problem for the particular person using the system. So if you go back thinking about the parallelogram that I showed you, if we had an expert mathematician, I would probably give them the system will probably recommend a high level integral solution to the problem. Whereas if we had a novice user, we might either choose a visual representation or an approximate representation, depending on the age of or the level of the user, which representation to use. So we basically have built algorithms and systems that can do this kind of analysis and recommendation. And we are trying to build these techniques into AI tutoring systems. Now, another area where I apply my work is in healthcare and in personalized medicine. So we're looking into how to integrate different data we have about an individual patient so that diagnosing and treatment plans recommended could be more personalized. So a lot of these models that we use are, in order to integrate these different modalities of data, are black box, so deep learning or other great black box methods, where we don't really understand why a system has made the recommendation. So we're looking into ways to extract explanations from these black box models. And we can use ontologies and concept reasoning to help us with this aim to build these into clinical decision support systems. In particular, we're working in oncology. And I think that AI will transform also how pharmaceutical companies work. For example, the drugs of tomorrow will no longer need to work for as large a proportion of population as possible. Now they'll be tailored just for me, my genetic makeup, my diseased cells, my personally suited chemical composition of the medicine. And they will only need to work for me and nobody else. And this will do away with really expensive and lengthy clinical trials and will allow for a much, much more responsive and personalized approach to healthcare. And in other areas of reasoning, let me give you just a glimpse of how machines are beginning to teach us, and where their reasoning is could be seen as surpassing the level of human intelligence. So I mentioned earlier the game of Go. So let me see. I'm sure that all of you, or most of you, will be familiar with the game of Go. And in March 2016, DeepMind's program AlphaGo challenged the world grandmaster of Go, so Lee Sedol, in a very publicly advertised campaign for $1 million. The match between Lee Sedol and AlphaGo. And Go is an ancient game that people have invested huge amounts of time into. And this guy is definitely considered to be like a Go genius and a bit of a god figure, really, in Asia. And why is Go so challenging? Well, Go has more possible board positions than there are atoms in the universe. Imagine that. So we're still learning. Thousands of years of people who have devoted lives, humans who have devoted lives to studying the game. And in this match, in game 2 out of 5, it seemed pretty much very similar to any other game until move 37. And AlphaGo made a move that really surprised the Go genius, the human Go genius. And it was a move that no human would think to make. I don't know if you watched the Asian commentators. I don't understand any of their languages, but you could see that everybody was like in shock why would AlphaGo choose this? And no human would think to make it. So why in 3,000 years of Go hasn't any human come up with that move? Why was it that it was surprising to them? Well, by playing itself thousands of times, AlphaGo had taught itself an entirely new strategy. And now there are thousands of people who are studying why that move was made and what was the intuition behind it. And AlphaGo has turned the tables on human learning, so to speak. So we are teaching machines our expertise, but machines are also giving us new knowledge and new insights and new intuitions that we can learn from too. Let me look at some other societal impacts of AI, but I'm only just going to briefly say a few words. Let me see how I'm doing for time, I think. So AI surrounds every aspect of our life. So it's not surprising that many people are concerned about what's going to happen to their jobs. And the most pessimistic studies, I think there was one coming from Oxford, predict that as many as 47% of jobs will disappear in the next 20 years. So will robots really replace us and take all our jobs, do these jobs better, faster, cheaper, in a more intelligent way? I don't think they will, but they'll change the way we work. So the AI system of the future will have a profound effect on what we do and how we do it, much like, I don't know, Industrial Revolution affected the manual jobs of the 19th century, and how the digital revolution is transforming how we're communicating in the 20th century, and now we have AI in the 21st century. So a lot of repetitive and menial work will disappear and be replaced by automated robots. I think this one is in the Tesla factory in the US. But this is no bad thing. I mean, many of those jobs are soul destroying and harmful for our health. And there's a shortage of people who actually want to do them. So, but what are the potentially threatened jobs? So, well, factory workers, for once, accountants, postal workers, delivery workers, lawyers, drivers, human translators. Anyway, the list goes on. So yeah, the jobs will disappear, but new jobs that we can't even imagine yet will be created. I mean, who would have thought that in 1950s, a software engineer would be a job of today? Imagine explaining that to your grandparents then. So what would the job of the future look like, and the future of our children? Well, I think that they'll have a lot to do with this intelligent technology and with traits that are inherently human, such as love, empathy, creativity. So, for example, nanotechnology specialist, memory augmentation therapist, personal educator, virtual reality creator, or actor. In fact, I met a woman a few months ago, and she had like the most amazing job title. Her job title was personality creator. So she was inventing different artificial personalities with specific traits, quirks, vocabulary, mannerism, sense of humor. And then these were used in the characters in gaming or in chatbots or other AI assistants. So very interesting. And as these systems become more ubiquitous, there are obviously many ethical and safety issues that arise. So who takes responsibility for a harmful decision made by a computer program? And for example, in law, courts in the US are already using AI systems to compute a sentence for a person that was found guilty of particular charges, especially when it depends on complicated and numerous factors, and machines are very good at that. So not if a person, so the systems are not deciding if a person is guilty or not, but when found guilty, the AI systems are deciding what should the sentence be. And and of course there are organizations that are looking at these ethical dimensions of intelligent systems and of technology. And obviously the Leverhulme Center for the Future of Intelligence that is organizing this workshop today is one of such places where people are employing or working with philosophers, theologians, psychologists, and computer scientists, engineers, and so on. And ultimately, there's no right or wrong. I think we will probably model machines on what the human would do. So evolutionarily, I think we are programmed to preserve ourselves, and this is our instinct. So I suspect that models will probably reflect that. And let me just mention another ethical aspect in the development of these intelligent systems, which is the bias that is inherent in the AI system. So the bias comes at least in two forms. One is in the lack of diversity of those that build these kinds of systems. And the other one, there is the data that is reflecting the societal bias. So one is in data, one is in people who are building these AI systems, machine learning systems. And there's research out there which shows that systems learning exhibit an unconscious bias of their creators. And this, data does not lie; it represents us as a whole of our society. So we need to study more. And in fact, I think that most of the leading companies are aware of this problem and are starting to address it. But obviously, a lot more needs to be done. And of course, there's research areas even within the Leverhulme Center for the Future of Intelligence, which is actually looking precisely at these issues. So, will AI and intelligent systems outsmart us or replace us? Will they be sort of a threat? I really, whilst I am building these systems that are behaving in intelligent ways like humans, that are finding intuitive solutions to humans, I really think that the future will remain in the hands of human experts, but we will be heavily supported and helped with these intelligent machines. They will assist us and they will collaborate us and they'll enable us to work more effectively, and as well as do things that are beyond our capabilities alone. So I really do think that all of the positives of the intelligent machines outweigh the negatives. And yeah, we're nowhere near like Terminator style future, but we're only, like a decade or so away from the future where we have AI helping doctors diagnose better and cure diseases more effectively. Like we are currently looking into using our system, putting into a clinical trial to predict the pathological response, completeness response for breast cancer patients. And we are really only years away from using personalized drugs where, drivers will drive more safely, surgeons will operate more accurately, and people can converse across multiple languages, and teachers will not be so much teachers as mentors that are directing self-learning. And so, of course, there are risks, as with any new technology, and we need to be aware of these risks. And when we are designing and deciding what's intelligent and whether it's beneficial for society, we need to be doing so in a mindful way, be aware of these risks, and consider these ethical aspects and implement them and mitigate against them. So, for example, we might be countering biases in algorithms and data, or producing explanations where a machine makes a decision about the human. And basically, I think that in this way, we are really ahead of really exciting times where we can use technology that is going to work for us and with us. And I think I'm going to leave it there. Thank you.